All right, so there's our goals for the day. Today we're going to be dealing with data tables. And we are going to be, I'm going to try to be really consistent about identifying delta x and identifying n, and then the x subs as well, to kind of help us out with the identification of those rectangles that we're really trying to make. So we are going to be given a velocity, and we talked yesterday about the relationship of velocity with displacement. So I'm giving you a table. Some of that data may be useful, some of that may be extra, but it's asking you to, number one, sketch a smooth curve passing through the data points. So I've given you a grid there. I'll give you a couple of minutes to do that if you haven't done so already. And then we're going to draw some pictures, and we're going to do midpoint Riemann sums for n equals 2 and n equals 4. So I'll give you just a minute to go ahead and get started on that, and we'll come back. All right, so let's start with n equals 2. If n equals 2, we're looking for the interval from 0 to 4. If n equals 2, that's the number of rectangles, right? What's our delta x? 2, right? I'll go from 0 to 2 and from 2 to 4. That'll be my delta x. So if n equals 2, I'm going to need x sub 0, I'm going to need x sub 1, and I'm going to need x sub 2. What's x sub 0? What's the first x value? First x value would be on the left end of the interval, would be 0. X sub 1 will be the first subinterval plus delta x, so that would be 0 plus 2, and then x sub 2 would be 4. Okay? Now, again, we're using a midpoint Riemann sum, and we have two rectangles. So using a midpoint Riemann sum, the area that we find will be delta x times f of x sub 0 plus x sub 1 divided by 2 plus delta x times f of x sub 1 plus x sub 2 divided by 2. What's that funny business inside the parentheses? What's the x sub 0s and x sub 1s and all that divided by 2? What am I doing? I'm finding midpoint. Okay. Do you have to write this notation every time? I don't think so, but I think it's worth getting used to what that's going to look like. I think that's going to give us a little bit more help as we move towards section 5.3. All right, so let's do some substituting. Delta x is 2, right? Can I just go ahead and factor that out? Would you be okay if I just factored the 2 out and did the rest inside? Is that all right? Taking that out of here and out of here. Okay. So this will be f of 0 plus 2 divided by 2. I don't need that extra parenthesis because I factored out a 2. I need to take that off. Plus f of x1 plus x2, that's 2 plus 4 divided by 2. Guys, I think there's easier ways to see this, but is what the arithmetic here and the substitution making sense? Okay. So this is 2 times the quantity f of 1 plus f of 3. Of course, I'm messing up variables again, guys, because this is v of t. Every one of these f's should be v's, guys. F of 1 plus f of 3. There's f of 1, I'm using f in place of v, and f of 3. So 30 plus 35 is 65, right? Twice that is 130. And since the problem is given to us in context, meters per second, we're looking for distance traveled, so our units will be meters. Okay? Good so far? Okay. Let's go to n equals 4. If n equals 4, what's delta x? I got to chunk 0 to 4 into 4 equal sized chunks, so delta x would be 1 then, right? Instead of 2? Okay. I'm gonna I'm going to leave this idea for now, and I'm going to try to do this a little bit quicker, because we now know. Well, let's do our x subs. What's the first x sub? What's x sub 0? 0. What's x sub 1? 1. What's x sub 2? 2. What's x sub 3? 3. What's x sub 4? 4. Do I stop? I stop now because my last x sub has to match up with the end value. Okay. Now, here's another way of visualizing this. Since I'm using a midpoint, I'm going to use the midpoint of all my x subs. So the points I really care about are 0.5, 1.5, 2.5, and 3.5. That gives me 1, 2, 3, 4 rectangles to deal with. Okay, you've probably seen it that way, but does that make sense? So really, my area now is equal to delta x times all of those function values, right? F of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5. Add up all those function values and multiply by delta x. What's delta x? 1. So we're going to add up f of 0.5, or in this case, again, I'm using f, but we really should be using v. I'm going to add up all of those function values circled in red. So 60, 95, 135. Check my mental math. Is that 135? Okay. Which one's more accurate? 2 rectangles or 4 rectangles? Which 130 again? Where'd I get the 5? Oh, I was looking at this 35 again. I was looking at the 35 I circled in blue. My bad. So it's 130 again. Which one's more accurate? Let's see, that makes my question bad. Which one's more accurate? They're the same. They're both pretty good. Could we do better than this? Yeah, how many rectangles do you want to make? 8. Could we make more than 4 rectangles? Pause. Look at the information you're given. Could you make more than 4 rectangles? No, because if you were to make more than 4 rectangles, we would be finding data values in between these two, and in between these two, and in between these two. And with sparse data, you can only use what you're given. You could use LRAM and RRAM with more rectangles. You're absolutely right. Good point. But you can't use an MRAM with more rectangles. Okay? How many rectangles could you do if you were doing an LRAM? Because you'd use all but one of them, right? So you'd use 1, 2, 3, 4, 5, 6, 7, 8. Yeah. You could do an LRAM with 8 or an RRAM with 8, but you couldn't do an MRAM with 8. Okay? All right, let's go to example 2. Again, like to give you things in different ways. Do you feel like you could describe the motion of the object over that interval from 0 to 6? Let's actually just take a minute, because this is probably the most challenging one of this bunch. So I just wanted to give you a minute to take a look at part A and how you describe that motion. All right, let's come back together and finish this up. Is the object ever stopped? No, because this is a velocity curve. What does a horizontal segment on a velocity curve mean? Moving at constant speed or moving at a constant velocity. So this object is always moving. In what direction is this object moving? It's moving forward, or whatever we determine to be the positive direction. So you might want to think about that as you're describing. The object slows down and then maintains a constant velocity, increases its speed, and then maintains another constant velocity. That's a brief overview, but I want you to be careful about some of the conclusions you draw, especially because this is a velocity curve. Okay? We'll move on to part B. Use geometry is good, to find the displacement of the object between t equals 0 and t equals 3. Is this a Riemann sum? No, it is not a Riemann sum. This is a geometry question. When you go from 0 to 3, you're finding this area, and because they're nice geometric shapes, you can find that area. There is a trapezoid. I think it's easier to use rectangles and triangles. Count the boxes. How many boxes are there? There's 11 and a half boxes? I see 3.5 boxes. How big is each box? I got you. I kind of get where you're coming from. How many boxes are there? Say 3.5. How big is each box? 10 what? 10 meters, right? So 3.5 boxes, 10 meters. This would be 35 meters. You okay with that? Okay. Part C. Use geometry again. Find the displacement of the object between t equals 3 and t equals 5. That's this one. We've got more boxes to count. I see 1, 2, 3, 4 whole boxes, right? So we've gone at least 40 meters. What's this last one? It's 1/2 times 1 times 20, right? 1/2, 1, 20. That's a triangle. Triangles are easier than trapezoids for me. So that's another 10, isn't it? So is that 50 meters? Well, that's 10, 20, 30. Let's do it that way. My box counting is inconsistent, but do you see where I'm coming from? Okay. Okay? Last question then. D, assuming that the velocity remains 30 meters per second, what does that do to the graph? It makes that velocity curve go horizontal forever. Find the function that gives the displacement between t equals 0 and any time greater than 4. Okay. What's nice about this situation that they allowed us to do to make this problem a little easier? The velocity is constant, and velocity is constant means we can add velocities, or we can add displacement at a constant rate, right? Constant velocity. What's the relationship between velocity and displacement again? Displacement is the antiderivative of velocity. Very good. So if velocity is constant, displacement will be if velocity is constant, think in terms of functions. If velocity is constant, displacement will be linear. Because linear functions have constant derivatives and backwards. You with me on that? So displacement will be linear. This will be linear displacement, at least in that direction beyond t equals 4. Okay? Good so far? So, displacement S of t is equal to if we're going to go beyond 4, let's draw a line here. Let's stop at 4. Up to the point of t equals 4, how much displacement have we gained? $55, I think, is right. Because we said 35 up to here, right? And then 20 more. So our starting displacement is 55. And then I'm going to add some linear relationship of velocity. Okay, so some of you are saying 30t. 30t. 30t is not a bad starting place, but is 30t accurate? No, because, and here's what I'm going to go with. If, let's say t was 1. Let's say t was 1. That means we would have 85 displacements, right? Displacements. We would have 85 meters of displacement at t equals 1, right? But at t equals 1, do we have 85? We do not. We only have that much. So your correction factor that I'm hearing you guys say is accurate. I need to subtract 4 from the time in order to actually get what I'm adding each second. Okay? For t greater than or equal to 4. Okay? Teaser for tomorrow. Tomorrow we are going to do trapezoids. And we're probably also going to have to introduce some notation with the integrand. The integral symbol is the same, but we are going to introduce the idea of a definite integral. So we're going to do trapezoids for areas and introduce some new notation, and there will be much rejoicing.